and we're going to learn about gutters and inlets. Here's the picture I shared earlier, and basically, when we talk about a gutter, this is what we're talking about. So this space between the pedestrian walkway and the actual road. And the idea of having a gutter is that it collects the runoff and it flows down in the gutter up until the next inlet is found. So here's an inlet, and then keeps going, finds another inlet. So you find some flow that is intercepted at the inlet, but also some bypassed flow that doesn't get intercepted and just keeps flowing. Another key concept is spread, which is how far between the walkway and the road the water in the gutter spreads. So that's the gutter spread. And also there's the concept of depth in the gutter. Okay, so since we have these terms covered, we're going to look at some typical gutter sections. Um, this is what we were looking at in the previous slide. So here would be the walkway and the road slope. Okay, you could have something that has a composite section, so that's the road slope, and then there is an additional, I think we call it gutter slope. You could have a curved section, which is defined by these equations, so you can do that. Basically, any gutter can be modeled in StormCAD. They're just modeled a little bit differently. You could have V-shaped gutters, a V-shaped median. You could have circular gutters and a ditch or median section. Okay, so different options. And let me show you actually in the software what we do with that. I don't know if you were here for this, Rodney, but it's a picture of what we mean by an in-sag inlet. The others we refer to as in-grade, on-grade actually. um, all right, I was going to show you the software. So we talked about gutters. We didn't have any gutters here because these inlets were all in-sag. I'm going to open um, just a sample file so we can play around with that a little bit. All right, so this is a picture that shows our inlets and it shows a gutter element here. So I'm going to turn the background layer off for a moment. So there's a gutter on each side of the road. And if we take a look at our gutters, we can have a user-defined, a catalog gutter. So let's take a look at the catalog. As I mentioned the other day, you can create your own gutters that you use all the time and then export them to a library that you can reuse for all your project. So here are different options. The conventional gutter is what we were talking about, that triangular gutter. Irregular would be something like this, where you input the cross section of that. Hold on, let me move that around here so we can kind of see both of them at once. All right. So even to model these, you can do irregular sections. You can have a trapezoidal, would be like that ditch that we were looking at. And in the conventional one, if it has that double slope, you can do a gutter depression. So let me go back here and I'll just show that one. So this would be conventional, and with an additional gutter depression would be something like that. All right, so these are the ways that we define our gutters. Let me go back. Okay, so now that we know the different forms of gutters that we can have, let's learn what gutters actually do. Well, in the gutter, we have the capacity for bypassing flow from one inlet to the next. So it really transports flow from one inlet to the other. That's its purpose. And in the gutter, we're concerned with the spread on that road, remember? And when you're doing the automated design, for example, you can set maximum allowable spread. And you can input and see gutter results at the actual catch basin inlet. So we're going to take a look at that. All right, so an inlet, or also called catch basin in the software, is the structure where we let the water into the underground sewer system. Its hydraulic capacity or efficiency depends on the physical characteristics of that element and also the flow in that gutter. In order to analyze inlets, we need to know what kind of inlet it is, what are its opening dimensions, what is the road slope, what is the gutter slope, and whether it's on grade or in sag as we had been modeling them. The inlets that you can have, so far we have had 100% capture in sag inlets that we didn't have to worry about. You could also limit the capacity. You can say, I don't know exactly what my inlet looks like, but I know it's going to be able to intercept X cubic feet per second. Or you can input a curve that says inlet versus flow captured. So flow that is coming in the gutter. So if you're seeing a flow in the gutter of, let's say, 10 cubic feet per second, the inlet can absorb 5 of them, and then the rest would become bypass flow to another inlet. So something like that. So really what we're going to focus now is that catalog inlet. If you're going to use the inlet catalog, I'm going to show you what it looks like. Where are my catalogs here? Catalog, inlet catalog. You can see that any catalog that you have is probably already here, and if not, you can set it with the flow to inlet versus flow captured. But the majority of inlets that exist are here. In fact, the software ships with a library of inlet for Florida, Connecticut, and Virginia. And I think these are yeah, just kind of generic inlets. So you can see here, let me just show you some options. Combination inlets, curb inlets, grate inlets. So let's just pick one of these and take a look at what that is describing. So you set the inlet type, in this case gutter, grate, width, length, and the type of grate. So whether it's reticuline or just parallel bars, etc. And it's width and grate length. So anything I'm going to show you, it's the description of all these inlet types, okay? Okay, so a grate inlet would look something like this. And it's an opening that's covered by a grate to, prevent solid objects from going into the catch basin. And they're very typical. They're typically installed on the road where you're seeing the flow. The direction of the grates coincides with the direction of flow. Problem with this is that they could clog, but in fact, in the software, when you're doing analysis or designs, you can set a percentage of clogging. So you can assume that, if it's during the fall when you're getting a lot of foliage, or if it's in a place where you're going to get a lot of garbage that falls in there, you can assume some percentage of clogging. Here are some examples of those descriptions. P50 is a parallel bar grate with spacing of almost 50 millimeters on the center. Here are some available grate types with different degrees reticuli. Other type of inlets are curb inlets. Let me grab my pen right here. So basically what it is an opening like this. So the water actually goes in through this blue spot right here. Um, you can specify all the dimensions, the length, the height, the width, and here are some recommendations for in-sag locations. And if you're doing it in an on-grade, that it would be less than 3% slope. So they're very effective when it's a flatter area. If you're doing it in a very steep area, then basically its ability to intercept is limited, right? Because the flow would just bypass it very quickly. Here's some of the information that you're going to be asked when you're inputting that information: local depression, depression width. So this is all specified in these graphs. So use this as a reference when you're doing your own inlets. There's a combination inlet, which is a combination of the two previous ones. So it has a grate at the bottom, but also on the side it has an opening. So it's great because it can do the same as the other two. There are also slot inlets, and it's basically something that looks like that. So it looks like a pipe with a cut on the top that it allows flow in that direction. You want to do this when you have sheet flow before it crosses onto the roadway. So you can see even perpendicular to the road a lot of these things. So if you have a very steep road that goes like this, and maybe it's meeting another road here, you can do slot inlets like that so that you're not going to see water coming from this direction. So yeah, their advantage is to intercept flow in a wide section. But the problem is that they can clog because the entry is very narrow. Other inlet types that you can use in the software are the ditch, flow to inlet versus flow captured, as I mentioned, and gutter depth versus captured flow. The one thing that I would warn you about using either of these two is that they're not, if you're doing an automated design where you want the software to figure out the correct inlet, it's not really going to be able to do that with these two types. Okay, we briefly talked about inlet efficiency. I showed it to you when we were doing the presentation on the design constraints because inlet efficiency is one of the design constraints. And basically, it's the efficiency is calculated as intercepted flow divided by the total gutter flow. And whatever does not get intercepted, we call it bypass flow or carryover flow. So you want an inlet that is as efficient as possible so that you're not just passing all the water on the surface. So when we're doing the design, we can set, okay, the, I want you to pick an inlet that at least has X percentage of efficiency. Okay, we talk about inlets on grade and on in sag. But when you have grade inlets on grade, we talk about frontal flow um, and also side flow. So let me see if I can draw this. So if we had our little street here, that's the walkway, and this is our road. And over here we have our grate. Okay. So the flow that is within the width of the grate, so the flow that goes up to here, is called the frontal flow. And anything beyond that is called side flow. So this would be QW. And if the flow spreads, it'd be QS, so side flow. Some of these numbers we give you just so that you can understand what it is that we're reporting on the software. Here's some of the equations. I'm not going to go into much detail because they're very self-explanatory. They have the variables, but this is how we figure out the flows in each of the inlet types. So if you have a Grate inlet on grade, this is how we calculate the flow that's, as I showed, frontal or side flow intercepted. Okay. I know it's after lunch, so we're not going to go over equations. But again, they're here for your reference so that you can understand what the software is calculating um, in all the scenarios. Here's a curb opening inlet on grade. So we remembered that it's the curb is the one that, if this is our walkway, not very good at drawing in perspective, but something like this. So the flow is going right in here, right? Through that opening. Okay, so obviously the efficiency is going to depend on the dimensions of that curb opening inlet. Here are all the equations that we use. And here's how we calculate the gutter cross slope. The efficiency here obviously is calculated depending on the opening and the lengths of that gutter. Here are some efficiencies, basically the same equation we just looked at, depending on the length of that curb. And here we have combination inlet on grade. We talked about grade and curb inlets. So we had already looked at those in the picture, so you know what it is that we're talking about. Okay, inlets in sag. Again, that was the picture I showed at the beginning of this presentation. We assume that the flow that goes in here does not escape, is always intercepted by that Grate inlet in sag or whatever inlet in sag that you have, and it goes into our system. And when you have either grate or curb openings in sag, they're calculated as a weir or orifice, and it depends on the depth of the flow. So if it's very shallow, the flow is going to basically go as if it were a weir, right? But if it's very full of water, then it's going to act as an orifice. And when it's operating as a weir, this is how we calculate flow intercepted. When it's operating as an orifice, this is how we calculate that intercepted flow. Here's how we calculate or how we divide the categories based on the geometry of the throat for the curb inlets. So as I mentioned, if it's very shallow, it's a weir. If the water is completely submerged, then the water is going through an orifice. But in between those two, it's a transitional flow stage. And this is the general equation for calculating that intercepted flow for those inlets. For orifice flow, okay, how do you know how far to put your inlets? That's a really good question, and one that we are asked to solve all the time. And the answer to that question is that it depends. It depends by the geometry of your site, but by the inlet capacity that you put in there. So if you put really large inlets, you're not going to bypass that much flow, and therefore you don't need them as close to each other. And it also depends on what kind of watersheds we have. If we're talking about completely paved surfaces that are discharging directly to our road, then you're probably going to need more inlets than you would otherwise. Typically, the way to figure it out is to trial and error. There are also regulations in many places that say you have to have, you cannot go for like 100 yards or whatever longitude in a road without having an inlet. So sometimes there's a maximum space that you can go without having an inlet. But more often than not is a trial and error process. And also it's kind of common sense, because if this is the profile of my road and I have something like this, you know, you know that at the lowest points you're going to have to place an inlet, because it's just logic. You know, the water will collect easier there. Um, so again, trial and error. And one thing that you can check for is the design spread. So let's say you started this design with one inlet here and another inlet there, and then you calculate your design, and then it turns out that the spread here goes like this far into the road, and you decide, no, 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 that's too much. Okay, I'm going to have to put another inlet in here to intercept my flow. And then you check for the spread again, and then maybe it's at an acceptable level. Okay. If you have, well, the geometric controls, you have to have an inlet at the uppermost point in a gutter if you are not complying with the gutter capacity criteria that you need to be meeting, like I just specified, the gutter, the spread. Where else do you typically have inlets? At intersections, because you don't want, let's say you have this intersection that looks like that. So typically you will have flow to prevent the water that's coming from here. You don't want that becoming a hazard all throughout, so you put an inlet right there. Typically you would have one there, one here, another one here, and so on. So to keep those intersections free of water. So at intersections, if you have a change on the slope, then you also want to put an inlet in that location. So if we have something like this and then like that, you know that at this location you're going to have to put an inlet, right? If you have a place where you have side drainage entering your street, so for example, you have the side of your road right here, and you have, you know, from a big building, the rooftop is discharging right there, for example. So ideally, you don't want that big flow to just circulate on your gutter and create a hazard. So you want to put an inlet right there. Low points, obviously, we talked about that. And before a bridge, you want to put an inlet as well, so you're not having water on the bridge. So spread, as we talked about, is a big criteria for designing and placing our inlets. And we talked about the spacing being a function of upstream bypass flow, the area that is drainage to it, and geometry of your gutters.
If you found this video helpful, please give it a like. If you want to see more such series, consider subscribing to our channel. Thank you, and see you next time.